So this is the measurement unit where I'll teach you how to round and calculate using the scientific method. So before I get into using numbers, let's talk about the difference between accuracy and precision. Accuracy refers to how close your measurement is to the correct answer, whereas precision would be how close are your data values to each other. So if I gave you a more pictorial representation, if we assume that the bullseye is the true correct answer, the first one has both good accuracy and good precision because all three match this value and all three are close to each other. So the precision portion would refer to the fact that these are all close to each other, and the accurate portion would refer to referring here. That's why the second version has good precision because look at how these three are all close to each other. So good precision, but it is nowhere near the center, so bad accuracy. And this last one, you can obviously tell nowhere near the target and nowhere near close to each other, so bad on both. Go ahead and pause the video and try to figure out whether these values are accurate and if these values are precise. Since all three numbers start with 45, 45, 45, I can definitely say that these answers are precise because they're all close to each other. However, this is definitely not accurate because the answer should have been closer to 48. So why am I talking about accuracy versus precision? Because if we didn't all agree on one way of measuring the accuracy of something or the preciseness of something, then we're all going to end up measuring things differently and we're all going to end up getting different numbers, even if we're measuring the exact same thing. So the way we correctly measure things using measuring devices is we read all the certain digits and then we read one more uncertain number in the measuring device. And that kind of doesn't make sense. Like, how do you measure something that you're not sure of? And what I mean by not sure of is you're just going to estimate the last number. And this is important because it tells scientists how many numbers could your measuring device measure. Because if we took a look at these rulers, all three of those blocks are exactly the same, but one of them is using a crappy ruler and the other one is using a very detailed ruler. So the way we read these is we read until our certain number. When I mean certain, I mean read the tick marks. What place value do the tick marks tell you? And so this first one right here, it goes from 0 to 10. So the tick marks are going to the tens place, which means that we are certain in the tens place. And so when I create my number line, I can be certain of the tens place. But when we measure using the measuring devices in science, we measure until one place of uncertainty, which means after the tens, we're going to estimate the next place value, which is the ones. That means these rest of these place values are not able to be measured using this ruler. So that means I'm going to go ahead and read my certain digit, which, I mean, honestly, the tens place doesn't even reach 10, so it's a 0. But remember, we don't really write zeros in that place value, so I'm going to leave it blank. And then I'm going to estimate the next place value, which to me is kind of in between, not quite half, but a little less than half. So I'll go ahead and estimate a 4. And then since these are rulers in centimeters, I would have to say the unit for this is centimeters. So if we go to the next ruler, look at how this next one, we're going to read the tick marks and we're going to say these tick marks go from 0 to 1, right? This is the 1 centimeter mark. So that means I am certain of the ones place. So that means when I read and write these numbers down, here's my number line again, I am certain of everything until the ones place, because that's what this ruler can read. But the way I report my number is to tell everyone I used a ruler that can read to the ones place. I need to go one more place after and estimate the next place, which is the tenths. That means any digits that come after, it's not possible using this ruler. So I can go ahead and say, okay, I am for sure that this reaches 1, 2, 3 centimeters for sure. So I am certain it's at least 3. but it falls between 3 and 4. So we're just going to estimate and kind of guess where this falls. Since it's closer to 3, I'm going to say 3.2 centimeters. So I'm going to go ahead and say 3.2 centimeters for this. And then this last one, this one, the tick marks are teeny tiny. These are the 10th place tick marks, which means I'm certain of the 10th place because that's what these tiny tick marks are telling me. So that means my number line, I am certain all the way until my 10th place. That means when I record this number, however, I need to go one place after, which means I can estimate the 100th place, right? So that means I'm going to read every number until my 10th place. So this goes all the way, so zooming in, this goes all the way from, this is 3, this is 3. So that means this one is 3.1, and this happens to fall right there at 3.2. And so I see that it's, do you ever see a slight hair above 3.2? I see kind of a bit of a black hanging off of it. So that means this goes a little past 3.2. So it's bigger than 3.2. So I'm going to go ahead and say that this is at least 3.2. That's what I'm sure of. And then I'm going to estimate, since it goes just a hair more than 3.2, I can go ahead and say 3.21 centimeters as my answer. But if you were saying, oh no, it was exactly 3.2, like if you're like, no, that looks exactly 3.2, then you can go ahead and say 3.2, but you have to add a 0 to say 3.2 because this measuring device records up to the tenths, and then the 0 confirms that this is for sure a ruler that measured to the 10th place. Go ahead and pause the video and write the answers of what you think they are. I'm going to go ahead and let you know these are probably volume measurements, so the unit should be in milliliters. But again, unless I've specified for this unit, because we are just starting out new, don't worry too much about unit unless I've specifically told you the unit. So hopefully you said that since these are the tens place tick marks, so hopefully you said this is probably around 30, I'm going to say 7 milliliters. And then for this next one, since it falls between the 36 and 37 tick mark, I'm going to say it's at least 36. But since it's the ones place tick mark, I'm going to estimate the next one to be like 36.5. This next one, this is really tricky because this one is 20 here, but 21 down here. So do you see how it's actually going backwards while these were going upwards? So that's why be careful, right? Make sure you're reading the numbers carefully. This is actually 20.1 as we go down. So that means this right here is 20.3 and this is 20.4. So it falls between those two numbers. So my answer is for sure at least 20.3. And then since it's closer to the 4, I'm actually going to say 20.38 as my answer. Okay? So the numbers in the black has to be exactly the same as mine, but the numbers in red can be a little different. It should be somewhere near it, but it really doesn't matter. So like I said, the beginning digits, those are our certain numbers, and then the last digit is our estimation because then it tells us exactly what type of measuring device did we use. Did we use something that was very detailed, can read to the hundredths or the thousandths, or did we use a measuring device that was kind of crappy and can only measure like tens? So like I said, we're all trying to become the same in terms of our calculation and rounding. And I know you're used to your teachers in the past telling you exactly what place value to round to, but now in science, you should always know exactly how many numbers to round to based on the numbers you're using. So what numbers we use to round is based on what numbers are significant in the numbers you're multiplying and dividing. So what constitutes a number to be significant versus not? And this idea you already know because hopefully you've seen in the past that your teacher has told you 0.1 is the same thing as saying 0.1. In terms of mathematics, these two number values are the same, right? So you kind of already knew that 0 is not significant. And that's kind of what I'm teaching you, but I'm letting you know that there are a few more rules than just that first one in science. So let's go through all the rules in determining which numbers are significant and which are not. So understand non-zero digits are always significant. So anything 1 through 9. So looking at these numbers, 4, 4, and 6 are all non-zero. So this is 3 sig figs. Doesn't matter if there's decimal, 4, 4, 6, all not zero. So this is 3. That 0 in the front doesn't count, so 1, 2, 3, this also has 3 sig figs. Leading zeros, as in zeros in the beginning, do not count, and that's what we just talked about, right? We just said this 0 doesn't count, so 6, 7, 8 is 3 sig figs. But understand, it doesn't matter where the decimal is. Any zeros in the front, as in if it didn't come after 1 through 9, then zeros in the front never count. So 0, there's no number in the front, no number in the front, right? There's no 1 through 9 in the front, so that's why all of those don't count, but the 3 and the 3 count, so this has 2 sig figs. These zeros also don't count, so this is 1, 2, 3, 4 significant figures. Captive zeros, as in the sandwich rule, that's what I call it, is any zeros in the middle all count. So I really just look at the first not zero digit and the last not zero digit, and I don't really think twice. Anything in between are all significant. So that 0 is significant, so 3. First digit, last digit, not 0. So anything in between, all significant. First digit, last digit, anything in between, all significant. So same thing if it was like 0.01200012, it doesn't matter. You look for the first not zero digit, last not zero digit, and anything in between all count. Zeros in the front never count, so this would be 6 significant figures. So this is where it gets a little bit trickier. Zeros that come after a non-zero digit, this is where we kind of start to get a little bit crazier. So zeros that come after only count if there's a decimal in the number. And it doesn't matter where. It can be in the front, in the back, just anywhere in the number. If you see a decimal, then that 0 after a non-zero digit counts. So 7, 6 count. And then that 0, we're going to look for a decimal, and there's no decimal, so that one does not count. So this has 2 sig figs. And I know you're thinking like, what? Like how these two are the same numbers? Is that a typo? And I'm like, no, it's not. That decimal actually makes a big key difference. The 7 and 6 are obviously significant, but that 0, because of the presence of this decimal, makes it significant. So this is actually 3 significant digits. And you're thinking, why? Why is that even a different thing? In terms of value, it's not. But in terms of data reporting, those two let me know that the first person's measuring device measures to the hundreds place, whereas the second person's measuring device measures to the tens place. So those two things actually tell a completely different story. And that's why a decimal in science makes a huge difference. And so even this third one, I know it's the same value, but since it's 7, 6, and since these two zeros come after a non-zero digit and there's a decimal, both of these zeros count. So this is 4 significant figures. These only have 2. Since there's no decimal, none of these count. So I'm going to go ahead and say this only has 2 significant figures. So understand there are sometimes that we don't do significant figures with numbers, and specifically that would be when they are exact numbers. So exact numbers would mean anything that was counted. So in terms of counting, like you can't possibly have 1/5 of a person. I mean, unless you're super violent, right? So you can't have parts of people, you can't have parts of like molecules, parts of anything that's counted that does not have decimal values. We say that there is an infinite number of significant figures, or we just say, no, these numbers we don't count in terms of how many numbers we round. And then scientific notation. Maybe you've heard of them, maybe you haven't. If you haven't, no worries, I'll go over it in a second. But scientific notation, any numbers that are in the coefficient are all considered significant. And so where is this coefficient? The coefficient is any numbers that come before the multiplication sign. So this would be 4 significant figures. This would be 6 significant figures. Go ahead and pause the video and try these out on your own. I'll go ahead and show you the answers in just a second. Okay, so here are the answers. Of course, if you have any questions about any of these, you can always come and ask me through email or in person. Scientific notation really is just an easier way to write numbers because it lets us work with very, very large numbers or very small numbers without having to write it out. Like this one right here, I mean, honestly, this is equal to, and you might be thinking like, oh my God, writing this versus this, it took the same amount of time. And yes, for something like this, maybe, but in science, we use this number a lot, especially in chemistry. And this number is this long. And so we can't possibly be sitting here writing this number over and over again. It's just much easier to work with a number like this. So that's why we use scientific notation. So a scientific notation has two parts, the coefficient, which is this red portion here, and in chemistry, and understand that this is for chemistry because this is chemistry class, our chemistry coefficient is always a single digit, then the decimal. So actually in physics and engineering, they actually do 2 digits and then the decimal and some numbers. Theirs looks more like this, but we don't do that because it makes more sense for physics to be working in like parts of tens. But since our numbers are more easier to calculate using in the ones place, we only have 1 digit, okay? So we're gonna stick to our rule of chemistry of just doing 1 digit. And then the exponent is however many powers, and this is how I remember it, is how many times did you move the decimal? That's the exponent, okay? So converting numbers to scientific notation is not that hard. Remember, the coefficient contains all the significant digits. So I'm gonna go ahead and look at this number. I see that the 265 are significant, and the way we write 265 in scientific notation is, remember, 1 digit 2 and then the 65 like this. So now that I've had this, obviously these numbers are not the same. Like imagine if your bank told you had $2.65 instead of 265,000. So to make this the same value, we have to include the times 10 to the power of however many times you move the decimal to look like this. So everyone hopefully knows there's an invisible decimal here, and to move it to here, 2.65, I'm going to move it 1, 2, 3, 4, 5 times. So this is going to be a 5 here, but I have to determine, is it a positive 5 or a negative 5? And since this is a large number, this will end up being a positive 5. Whereas this bottom one, I have my 2.73, because remember, all those zeros don't count. The 2.73 are my significant figures. I put a decimal after the first digit. So then I'm going to see how many times I have to move the decimal to look like 2.73, so I know what exponent to put on top of the 10. So I'm going to move it 1, 2, 3, 4, 5 times. So this is the same 5 times, but this will be a negative 5 since this number is a very small number, a number between 0 and 1. So you should also be familiar in going back and forth. So how do we go back to standard notation? Pretty much move the decimal. So remember, positive exponents means this number should get larger, and the way we make the number larger is we move the decimal that way. So we're going to move it 6 times. 1, 2, 3, 4, 5, 6. So it's going to be 5, 1, 4, 2, 1, 2, 3, and decimal there. But how do we have these place value holders? We're just going to simply add zeros in there. This is going to look like 5142,000. And then a common question I get asked is, should you put a decimal there? And I'm going to go ahead and let you know, in large numbers, no decimal. We don't put decimals because it's just, there's no need, right? Then if we do the next one, this is a negative number, so the number should get smaller, so the decimal is going to move in that direction. 1, 2, 3, 4. So the decimal's here. So that means I'm going to say 0 point, because the decimal is there, 0.0072 is my answer for this one. So now I'm going to show you how to round. So if we're rounding using significant figures, I mean, hopefully you've known this already. If the number that comes after that number you're rounding is greater than 5, you go up by 1. And if it's less than 5, then we round down. So like I said, the sig figs tells us how many numbers to round. So I'm going to go ahead and see that this one wants us to round to 4 sig figs. So this is 1, 2, 3, fourth significant figure stops at the 4. That means the rest of the numbers needs to round into my number. So the 5 is going to round into the 4, 1, 2, 3, and then remember 5 rounds the 4 up to a 5. So there are my 4 significant figures, and then rounded up to 1, 2, 3, and 5. This next one's a bit tricky because it wants 3 significant figures. So 1, 2, 3. So I got to cut it off here. But the problem is if it's 1, 0, 0, that's only 100, which is nowhere near 10,000. So I guess I could make the rest of them 0, but then that's also a big problem because how many significant digits is this? This is only 1 significant figure because none of those count. So what we're going to end up having to do is not write it like this. When you get stuck on a number like this that's very difficult to write in terms of significant figures, this is where you implement the scientific notation rule. Because I only want the 100. So I'm going to do 1.00. That's all I want, scientific notation. And then I'll write times 10, and then I moved it 1, 2, 3, 4 times to get it after the 1. So 1 times 10 to the 4 is how I would report this number to the correct number of sig figs. Why don't you try the rest of these on your own, and then I'll show you the answer in a second. So here are the answers. If you have any questions about any of them, of course you can ask me in class or email, but let me know if you have any problems. So now we're getting into calculating using significant figures. Like I said, the way we round is very different than how you're used to. And I know your teacher used to tell you only round once, but actually in science, we are actually permitted to round multiple times throughout our calculations. And the only time we can do that is if we switch functions. And so the first type of function is multiplication and division, and these are considered one of the same kind. So if you're multiplying and dividing numbers, just keep multiplying and dividing and don't round until the end. And the way we round multiplication and division numbers is we just round to the least number of sig figs. So what I'm going to do is I'm going to multiply 1.34 times 0.04. That gives me 0.0536 in the calculator. But we have to round this to the correct number of sig figs. So what I'm going to do is I'm going to count the sig figs. This has 1, 2, 3 sig figs. This has only 1 sig fig. So between 3 and 1, we're going to round to the least number of sig figs, which is 1. So I'm going to round this to 1 sig fig. The zeros in the front don't count. There's my first sig fig, so I'm going to round to the 5, 0.05. But if I reported this number, this would be considered wrong because remember in science, if there are units, you have to include the units. And since I'm doing centimeters times centimeters, my unit would be centimeters squared. So this next one also has 3 numbers, but it really doesn't matter how many numbers you're multiplying and dividing. These are considered the same things. So if you're multiplying and dividing, go ahead and multiply and divide all of those together. So I'm going to multiply 3.456 times 8.32 divided by 9.4 in the calculator. And that tells me 3.058927, so many numbers. So once I have that, I'm going to go ahead and see that this one has 4 sig figs, 3 sig figs, and 2 sig figs. So my answer is going to round to 2 sig figs. So this answer is going to be 1, 2, and I'll cut it off at the 0. But the 5 is going to round the 0 up to 3.1. And then my unit will be milliliters times milliliters divided by milliliters, which means milliliters cancel milliliters, and I'm left with just a singular milliliter as my unit. So like I said, if you were to switch functions, you can stop and round. And what I mean by switch, it means if you are going to switch from multiplying and dividing to adding and subtracting. So the reason for that is because adding and subtracting, weirdly, is actually more difficult than multiplying and dividing in science. Because when you add and subtract numbers, it has to be based on place value. You have to look at the last digit that's significant, and you have to look at that last digit's place value, and whichever one, and this is weird, it says least, but whichever one is the least precise, as in higher value, because the higher the value you get, the less precise you're being, because the more decimals is obviously more precise, more detailed. So what I like to think about it is think about money. So if someone was offering you a value of $100 or 10 cents, what would you prefer? Okay, hopefully you're thinking the $100, right? So let's look at this, okay? So if I add 100 plus 2.3 in the calculator, I get 102.3. But we are adding. So instead of counting sig figs, we're going to look at the last digit that was significant. So this one's significant, but these are not. So my last digit of significance is in the hundreds place. This is significant, that's significant. So my last digit of significance is in the tenths place. So ask yourself, do you want $100 or 10 cents? And we want $100. So we're going to round our answer in the hundreds place, which is right there. So I need to cut off the rest. So clearly 1 is not in the hundreds place. So I'm going to place zeros in the rest of the values to make it the same value. And then that would be my answer in grams. Okay, we're basically saying if you add 100 grams plus 2.3 grams, that's 100 grams. It doesn't matter about the 2.3. It's such tiny values. I actually prefer adding numbers vertically instead of horizontally like we just did because it lets me see exactly what place value this ends on. So this number ends right there, and right there. So can you see the highest place value is right there? So that means my answer is going to round to the highest place value based on those three. So I'm going to go ahead and add 5.6839. So my answer is going to cut off there. So my answer is 5.68 and then meters as my answer. So like I said, we never just do one simple calculations. We're always doing multiple things at once. And if you're doing multiple orders of operation, you're going to follow the order of PEMDAS. Hopefully you've heard of PEMDAS. PEMDAS tells us to do parenthesis first, then multiplication and division, and then adding and subtracting last. So if we looked at this, we're going to basically do this first, and then once we have those numbers, we're going to multiply all of them together later. Okay, so let's do that. But what you have to understand is, do you see how inside the parenthesis, we're having to add? So that means if you were to add, and then you're going to multiply, you need to stop and round these numbers from adding. And then you're going to multiply and round again because there are two separate rules for both of those kinds of functions. So I'm going to go ahead and add 3.532 plus 0.6, which gives me 4.132 in the calculator. And like I said, using that number, I'm not going to add and subtract anymore, which means I need to stop and round. So when I round, I'm going to go ahead and round this from 3.532, which is the thousandths place, 0.6, which is the tenths place. So my answer needs to round to the tenth place. So this is going to be 4.1 when I round this number. So keep in mind, once you've rounded, all the numbers in the past don't matter. So we're never going to look at those numbers ever again because we've rounded those numbers away. And now this is my new number that I'm using to multiply with the rest of them. So when I now multiply 0.00382 times 0.7432 times 4.1, I get 0.01164 in the calculator. And using the new numbers I have, I'm going to use those to round to sig figs because I'm multiplying. So this is 3 sig figs, 4 sig figs, 2 sig figs. So I'm going to round it to 2 sig figs. No sig figs there. So 1, 2, round there. 0.012 would be my answer.